Hello everyone, and welcome to today's tutorial on the van der Waals equation and the behavior of non-ideal gases. Today we will be discussing the van der Waals equation, how we can derive this equation, the significance of the A and B values, and what it can be used to calculate. So to start off, what is the van der Waals equation? The van der Waals equation, which is named after the Dutch physicist who created it, stems from the ideal gas law, PV equals nRT. However, the ideal gas law is often unrealistic because most gases do not act ideally. However, van der Waals equation considers this fact. So van der Waals came up with an equation to account for it. It states that the pressure plus a constant A times the number of moles squared over volume squared, all multiplied by the volume minus the number of moles times a constant B is equal to the number of moles times the gas constant R times the temperature. So, how do we get this equation in the first place? Well, we know that it comes from the ideal gas law, which is pressure times volume is equal to number of moles times the constant R times the temperature. However, this equation for ideal gases is not a reasonable scenario. This is because the ideal gas law assumes that the gas molecules have a constant kinetic energy and that they interact with the sides of the container, but not with each other. However, we know that this is not true most of the time, since gas molecules are constantly moving and colliding with each other, which can cause a change in kinetic energy. We also know that molecules have attractive intermolecular forces between each other, which can cause a slight variation in pressure, which the ideal gas law does not account for. So what can we do to fix this, since most gases do not act ideally? Well, we must account for the change in volume that the real gases take up and the pressure that the real gases cause by using the constants A and B. The A value is used because sometimes the pressure of real gases is smaller than the ideal pressure due to the attractive forces between molecules. The V minus NB term is used because the real volume is equal to the ideal volume minus the real volume. It's also worth mentioning the fact that this equation works well for gases at high temperatures. Another important part of real gases is their compressibility factor. A compressibility factor refers to the difference between the values that you would get from using the ideal gas law instead of the van der Waals equation. Ideal gases have a compressibility factor of exactly 1, whereas real gases deviate from this. The closer a gas's compressibility factor is to 1, the more closely it behaves similarly to an ideal gas. For example, when looking at figure 6.5 from the textbook, we can see their compressibility factors of nitrogen gas and carbon monoxide are 0.998 and 0.997, respectively, which are very close to 1, so they act very similarly to ideal gases. And looking at the bottom of the chart, SF6, also known as sulfur hexafluoride, is the farthest away from 0, at 0.880, so it is the least likely to behave like an ideal gas. So far, I have talked to you a lot about these constants A and B, but what do they really mean? Well, these constants are known as van der Waals constants. A represents the intermolecular attraction between particles in a gas molecule, also known as the attractive force between these molecules, and B represents the volume that the gas particles occupy. The closer these constants are to 0, the closer they become to behaving like real gases. These values are always positive, and let's take a look at what they can mean. So when we look at figure 6.5 from the textbook, we will see that when looking at A and B, an ideal gas has a value of 0. This makes sense because we would not need these A and B values when working with an ideal gas. Okay, so now that we know more about where this equation comes from, what it means, and why we use it, let's jump right into a practice problem. Okay, so the question states, ammonia gas at 3 moles takes up 957 milliliters of space at a temperature of 64 degrees Celsius. What is the pressure of the ammonia gas in bar using van der Waals equation? Use table 6.5 when finding values for A and B. So the key thing to remember when doing these questions is to really watch your units, or else your calculations may be off. Table 6.5 gives us the van der Waals constant in bar times liters squared over moles squared for A and liters per mole for B, and we want our final pressure to be in bar. So that's very important to keep in mind when we try to attempt this practice problem. Alright, so first things first, we're going to need table 6.5 from the textbook to find our A and B values. So let's find ammonia on this table, and as you can probably see, the A value for ammonia is 4.225 bar times liters squared over mole squared, and the B value is 0.0371 liters per mole. So before we begin, we should always write down all of our variables and the proper units for each of them. So we know our A and B values from the chart, and looking at the question, N is equal to 3 moles. Now, here it's very important to keep track of our units so that our calculations aren't thrown off. The problem gives us a volume in millimeters, so we must convert that to liters. So our volume would be 0.957 liters. Next, they give us the temperature in degrees Celsius, so we must convert that to Kelvin by adding 273 to 64. Therefore, our temperature will be 337 Kelvin. And now, here's the part where our units become extremely useful. The ideal gas constant varies slightly based on what units we're using. So since our temperature is in Kelvin, our volume is in liters, and we want to find the pressure in bar, we will use the gas constant 8.3145 times 10 to the negative 2 liters times bar over Kelvin times mole. Okay, so now that we have all of our variables, it's time to try and tackle this problem. Although we could just sub in all the numbers first and worry about the variables later, it's much more efficient to isolate for pressure before we begin. So first, we're going to divide nRT over V minus NB. Now to isolate for P, we're going to subtract A times N squared over B squared from both sides. So now this leaves us with the equation P equals nRT over V minus NB minus A times N squared over V squared. Now we simply sub all of our values into the equation and solve for pressure. Calculating this, you should get the answer that pressure is equal to approximately 57.9 bar. Okay, so let's recap what we learned in this tutorial today. So, first we discovered what van der Waals equation is and how it comes from the ideal gas law. We know that the A and B values represent the attractive forces between real gas molecules and the volume that these gas particles take up, respectively. We learned about the compressibility factors and how a gas with a compressibility factor farther and farther from 1 means that they deviate from the expected values of the ideal gases more and more. We also saw an application of this equation and how to solve a simple problem using the van der Waals equation. So thank you all for joining me today, and I hope you have now have an even better understanding of the van der Waals equation and the behavior of non-ideal gases. Thank you so much and have a great rest of your day.